What's up, everyone? You've probably heard of test time compute before. What if LLMs could think and reason while you sleep? That's what this latest paper from the team over at Letta is basically proposing. So, Letta is a memory store essentially for LLMs. They started as a paper and now they're a full fledged company. You should check them out. And so, this paper, Sleep Time Compute, Beyond Inference Scaling at Test Time. And so, basically, what we're going to get into is we'll go through the paper. I have some other notes and some figures to kind of make this a little bit more easy to understand as well. And we'll see what we can figure out together because it's pretty cool. So, generally speaking, this is looking to sleep time compute is looking to attack the inefficiencies of test time compute. So, test time compute is when you're using a reasoning model and it does that thinking step. And in ChatGPT and all these other chat interfaces, it shows you what it's doing, it's thinking, and then it gives you an output. And this is the same in the API. And this sometimes can be quite long, so it can be high latency and inference cost to do this. It could be many minutes for some certain tasks. And so to combat this, they introduced sleep time compute, which allows models to think offline about the context before the user queries are actually sent, before the prompt is sent. By anticipating what queries users might have, they pre-compute from the context that type of information, reduce the compute required at test time. Blah blah blah. Reduce it by same accuracy, 5x less tokens. So let's jump into kind of this overlooking graphic. So zoom in. Nope, that doesn't work. All right. So some raw context. Sleep time. You would basically send all the context. So imagine you're working on like an app that looks at people's code bases, or maybe there's many files. And so at sleep time, you would send all the context, the code base, the files, the conversation history. And what you would do is send it to an LLM with a specific prompt, which we will have and we'll look at in a second here, that would basically pre-compute certain pieces of information that you think your user would be asking about. So it could be if we have like a financial chatbot during sleep time, we could send all of the latest financial documents about a company to and run a prompt that will extract certain financial quantities or metrics or things along those lines. This is especially helpful if we know the types of queries our users are asking. And so we can then get this really condensed kind of high level summary with specific points that we know users are going to ask and prepend that to the user prompt rather than having to do all of the reasoning over the whole context. So it's kind of like looking at the full context and creating like a condensed summary based on some logic of what you think users will ask for. So it's not quite like prompt caching because you're not caching the whole context. You're creating a new kind of condensed context, and it's not really like RAG because you're not really doing any like semantic retrieval. So that's generally how it works. We'll scroll down a little bit here. Yeah, it's especially helpful if the user is asking multiple queries about the same context because you can reuse that prepended like dense summary. So during sleep time, we were given context C, but not the query. Using just the context, we used an LLM to infer likely questions and reasons about the context, producing a more represented context. And so, yeah, it's basically taking huge context. We know we're going to need specific pieces of information from that based on our users' patterns and questions. Let's make a condensed version. Yeah, they test a bunch of models. They do a bunch of data sets. And essentially across the board, they see pretty much better performance at lower test time tokens used. So less tokens used at test time to get a similar level of performance. And so, for example, you're seeing here, this is Amy. Yeah, this is Amy. So with test time compute, the blue one, it's able to get this level of accuracy at 4,000 tokens of test time compute versus the normal version doesn't get it till about 6,000. Over here, this level of accuracy at about 3,800. Normal version doesn't get that level until about 4,500, so on and so forth. And there's some cases where the like non-sleep time compute version doesn't ever reach the same level of accuracy like we're seeing with R1 here. Here's a much more demonstrative case where with Claude 3.7 Sonnet gets to this level of accuracy at, whatever, 11,000 tokens. Without sleep time compute, it firstly never gets to that level, but it gets close to that level only around 20,000 tokens of test time compute. So this is showing how it can be much more accurate with much less tokens, which means less cost and lower latency. And there's a bunch of other kind of graphs to kind of help demonstrate this across different data sets. Let's see. This is just running it many times always results in better output. So if you could make more of those condensed summaries, it's going to have a better performance. This is something that kind of came to mind when I was reading through this. It's like, how do you know how to create that, what you need for that dense summary? The more predictable the queries are, the easier it's going to be, the more benefit you'll get. So again, back to that financial chatbot, if we know people are always asking about like the last quarter's like revenue growth, that's a very easy thing for us to extract in the sleep time compute prompt to then always have that in that little condensed summary that will prepend. So the more predictable, the more you know about the typical user queries you'll get, the more likely this will work. All right, cool. Let me just go back over to the notes here. So yeah, high level, sleep time compute is a technique that lets an LLM pre-process its context during what they call idle time, which basically just means ahead of time before the user asks its question. So it can answer the questions in fewer tokens. Like I said, it's not quite the same as caching, not the same as RAG. There's some overlap. When should you use it? So if the context is long-lived, so if a user is always working with the same code base, that's a good use case. That context is being reused again and again, having multiple queries to it. If you're trying to make things faster or save more money, and if the queries are predictable. So these are all situations where sleep time compute could help. The prompt that they directly from the paper. So you are offline memory, blah, blah, blah. Your task is to reorganize, consolidate memories by calling the rethink memory tool at every single step. We'll look at the tool in a second. Do this until it's done. Core memory provides an essential foundation context for keeping track of your persona and key details. Read-only blocks. Human sub-blocks store key details about the person you're conversing with. Prioritize the new information over existing memories. So, there'd be like new context passed through to this prompt, and then it would have to basically use this tool, rethink memory, to decide which one gets stored. So that's generally kind of what that flow looks like. Here's the tool, the rethink memory tool. Reevaluate the memory in block name, integrate new facts. So yeah, model gets sent new information. It uses these tools to say, hey, should we keep this or should we not? You can run this as many times as it needs, and then this one is the finish thinking tool, I believe they call it, and then that ends it. And a bunch of graphs we already looked at. The SWE futures case study is interesting. So it's a slice of SWE bench, and we'll just run through it real quick. So agent gets a repository, 7-file PR, then has a new issue flag, 6-step repair prompt telling to explore certain things. For baseline, the model sees everything. So the files, the directory, PR description, the repair plan, and then it can go and kind of do everything it needs to do. Let's go explore the repository, things along those lines. For the sleep time compute, the model sees all that raw context plus a prompt to go explore the repository. And then at answer time, the model sees both the raw context, so that's being passed as well, but also the condensed summary that was generated during idle time. And it's able then to perform at a much higher level on average 3,000 less tokens needed in its reasoning when producing the same answer. So again, huge time savings, huge latency savings. It's pretty interesting because really what this boils down to is a prompt, right? This is just a very interesting way to generate and persist context. So there's definitely some more interesting logic with the tool use, but really you're just using a prompt to say, hey, I know users will be asking about this, so let's try to use this very kind of condensed summary rather than giving the whole context every time, which just kind of goes against maybe some of the things we're seeing and talked about recently with larger context windows and just shoving everything in the context window. So awesome paper, be linked below. Hope you enjoy this, and we will see you next time.